Time seems to go really slow when you're waiting for class to start. Almost there, folks. Well, I guess we can start. Welcome back, folks. I appreciate everyone making it in today. It can be hard to come to class right before a long holiday, a long weekend. But any questions at all, folks, to start us out? Okay, I don't have too many announcements. It's kind of business as normal today. We're going to do lots of integrals, see how far we end up in. But the thing I did want to mention is we have our first assignment coming due, and that means grades are going to be starting to upload on Moodle on a regular basis. Typically, I try to get my grading done on Friday. I might get some done on Tuesday, but that means grades will update either on Friday, potentially Saturday or Sunday, whenever the grading gets completed. You'll know if you emailed me a homework assignment when it gets returned. You can assume the grades are already up in Moodle. So definitely double check if you're in the Moodle site right up here, just on a regular basis. Make sure everything looks about right. Sometimes I have made grade mistakes, and we always want to get those cleared up as soon as possible, not just for this class, but all your classes. Aside from that, let me see here. I think we're kind of out of announcements. That's amazing. Any last questions at all, folks, before we jump back in? Once I figure out where to put this, there we go. Okay, maybe one additional thing. I think I did put in somewhere here. Another one of those worksheet things. We did kind of an impromptu one at start of class just to show how that goes. If you feel like that's helpful for you, not everybody studies the same. This is kind of brutal rote learning, but if that's helpful for you, you can print out some of these kinds of things, make up your own. And it's also my way of saying these are the things that come up all the time. If you get these down pat, it just makes everything else in calculus much more streamlined. In essence, you're focusing on the new concepts, right? Not trying to look up what is the antiderivative of a cotangent. So these are all good things to have. Below some trig practice as well, just to kind of reinforce those skills. They always come back, whether you're in calculus 1, 2, and 3, and so on. So for the moment, we're here working on these kinds of integrals. And these sort of things are usually pretty nasty. Sometimes a U substitution can work, but that U substitution might take a lot of ingenuity, refiguring, a lot of ad hoc algebra out of nowhere. So for these kinds of integrals, another great method is a trigonometric substitution. We mentioned before, this is a pretty good review of trigonometry in its own right. All we have to do is decide for the square root expression in our problem, what form does it seem to match the most? We have a constant minus a variable squared, and that would fit in with this one. Notice this one's backwards. If you see the variable squared minus a constant squared, we really ought to use secant. But our problem fits this scenario, like on example 1. So we're going to see how to do this again on a new problem where there's something other than a 1. We have a 25 now. And actually, this problem is a little bit harder than the first problem because this integral is indefinite. It means we now really have to unwind our substitution. But here's how it starts. We select our substitution from right here in yellow and write, once I pick a color, x equals something sine theta. Anyone spot the value for a in this problem? Good call. Usually it's not too much work. You just take what's here, it's square root, and you're in good shape. Yeah, question? So, it would be a little bit just kind of inconvenient. So if it was a 13, you'd have to go square root 13 right here. So kind of the essence of what you're doing each time is just taking the square root of whatever you've got on that constant position. Yeah, 13 would work, but now the numbers are just going to be kind of wonky. Other questions so far? Okay, now that we have the x, the next thing you'd want to do is, well, we need to calculate our dx, so we'll do that right here. Just like we did on the first day of class, notice we've done like something about 50 differentials. I've lost track, but here's another one. Dx is going to be 5. Derivative of sine is a cosine theta. D theta. Last thing I'd probably take a look at is the thing that's in the square root. We need to simplify that down. So this is the algebraic bit, 25 minus x squared. We have a substitution right here for x by our initial substitution. So this becomes root 25 minus. Square this whole thing and you get 25 sine squared theta. This is a good check for consistency at this stage because the number here and the number here, that coefficient, should match. We need to factor it out so that this identity is back on the table for us, highlighted in yellow. Good news is you can factor out of the square root. This would become root 25. Some people just put a 5 there, multiplied by a root. 1 minus sine squared theta. So that's our next step. Then we're pretty much there. Just take the root of 25. We've got a 5 here. Let me space that out better though. Root 1 minus sine squared is just taking the root of cosine squared theta. But we know from our discussion on the other example, if the range is from here to here, cosine only takes positive values. And so the square root of cosine squared drops the absolute value sign immediately. I typically just move from here and write 5 cosine theta. But we've got it, folks. We can re-represent x squared. We know what to do with the root. That was this long computation coming down here. And we've also got a dx. We just need to throw everything together at this stage. Well, any questions with the initial analysis? Okay, then, like so many other things in mathematics, we just make a whole bunch of substitutions. Let's go in order. For the square root portion, let's maybe just leave the yellow highlighting for that bit. We're putting in 5 cosine theta. Now we're down below where we have an x squared. For that x squared portion, we're throwing in the square of this, so 25 sine squared theta down below. Finally, it's multiplied by dx. So let's go over here. Dx is now 5 cosine theta d theta. And we did it, folks. That's maneuvering all the way through the trig substitution. The new integral we have is now a trigonometric integral, or back in section 7.2, in other words. Any questions at all, folks, on those initial steps? Okay, this is where it gets a little dicey, just starting it off, getting through all of this kind of work. But once you're here, it simplifies a whole bunch. So let's see what happens. First, the numerator does involve a 25, so we have a cancellation going this way. Last, we have cosine times cosine for cosine squared divided by sine squared. So the integral is now cotangent squared. Theta d theta. And that's a little bit unfortunate because it's not direct on what is a good antiderivative for that, but there are a whole bunch of identities that are going to help us out. We saw something like this before when we integrated a tangent squared. So let's put down just a couple trig identities that we're going to need. We have this good old one, 1 plus tangent squared equals secant squared. Take that and just swap it to cofunctions and you have a right identity. 1 plus cotangent squared theta equals cosecant squared theta. Well, we want to substitute out a cotangent, so just subtract 1. Cotangent squared theta is cosecant squared theta minus 1. It seems almost unfair. This is simple, but the antiderivative is hard in that format. This is more complex, but the antiderivative is immediate down there. So that's a substitution we should make again through the trig identity. Integrate cosecant squared theta minus 1 d theta. So now that integral is even a lot friendlier. Anyone recall this antiderivative, cosecant squared? What would that be? Good call, negative cotangent on that one. Good catch with the negative as well. Reason for that is derivative of cotangent is negative cosecant squared. So that extra negative sign in the front is just to arrange positive here when you differentiate. I'll go do this one. This one becomes the variable theta. And now we need to take this whole entire quantity. Oh, hang on. Forgot this is a indefinite integral. We need to take that whole quantity and add a constant c. Those parentheses were not meant to be there. So it's looking good so far, but if this was a, let's say, 5-point problem, we could lose 2 points this time because undoing the substitution is very fundamental to this, and it's a decent amount of work on its own right. What we mean by that is, if there's a dx right here in the integral, our answer also has to convey a variable x. So use this information to undo that substitution. Any questions at all, folks, before we begin that last phase? Okay, let's move that down and out of the way. Probably want a little border. This is what I would do on the immediate next step. Start back right here, x equals 5 sine theta. I'm going to change the order, 5 sine theta equals x, divide by 5, so we isolate sine theta. We now have sine theta equals x over 5. And for the folks who are thinking about SOHCAHTOA, the hint from last class, here's where it actually comes into play. Let's just put this down. SOHCAHTOA, and we'll explain that as we use it. It's my favorite trig mnemonic. When we have this arranged here, this is going to be equal to, for a sine function, the opposite is in the numerator. For a right triangle, the hypotenuse is in the denominator. And here's our right triangle. We're going to use this right triangle to very quickly find an expression for cotangent, and we can get one for just theta itself by taking sine inverse right here. But let's start with that by building the right triangle. So sine theta is x over 5. If we say opposite and hypotenuse, we need an angle where that's relative to. So there's the angle theta. Opposite of that theta is x. The hypotenuse is 5. And now you can use Pythagorean's theorem to find this length. But there is a really, really rad shortcut to this that I would encourage you to take a look at. That right there is the missing length without even using Pythagorean's theorem. Let's do Pythagorean's theorem from scratch this once to illustrate that. But that is a pretty good shortcut for this kind of problem. If everything is going according to plan, no mistakes, you should have that same quantity right here that was in yellow. But let's check it out. I'll delete this in a moment. You would say that c squared is a squared plus b squared. The c is a 5, so 25 would be equal to a squared. I'll let a be my unknown side. B squared would be the x squared. So we would get a squared equals 25 minus x squared. We would square root both sides, and sure enough, that is exactly what comes out every time you use Pythagorean's theorem in this situation. So here's, once again, root 25 minus x squared. Does that make sense to folks on how to get that, either through the shortcut or for the quick Pythagorean theorem approach? Yeah.
Are you saying that it will always be that, the original function? Or is it...
Part of it, yeah. The part that we were substituting out, the trig substitution right here, is the missing length, yes. Kind of cool as a little trick. But you know what? Doing Pythagorean's theorem, that's an extra check of consistency. So if I did make a mistake, it's not coming out right down here, I know something was messed up. Maybe the substitution, some simple mistake. So the shortcut's nice, but this is a double check doing it that way. Other questions at the moment? Oh, the SOHCAHTOA was relative to this right here. S is for the sine function, and sine involves the opposite, that's the O in SOHCAHTOA, divide by the hypotenuse, the H. Likewise, cosine is the adjacent side, that one, divide by hypotenuse. And this is saying tangent is going to be equal to the opposite, divide by the adjacent side. So we'll practice that as we go through these notes as well. Other questions so far? Okay, let me clear out the scratch right here. And, well, let's throw this all in. Negative. Well, what's cotangent? Well, we know tangent is going to be the opposite divided by the adjacent. Cotangent's a reciprocal function, so it just goes the other order. Cotangent is going to be the adjacent side, root 25 minus x squared. Divide by the opposite side, that x there. So that's how we get our cotangent on this one. You simply take what tangent would have been and just flip it. Let's pause right there. Does that make sense to folks on getting the cotangent function here? Okay, now we're on the theta. Anyone see how we would get theta out? Oh, hang on. This was a negative cotangent squared. Yeah, I totally missed that in this problem. Thanks for spotting that. Should have came in like that. Or hang on. No, there's a other mistake here. That power 2 is a mistake. The derivative of cotangent alone is cosecant, negative cosecant squared. That should have been to a power of 1. That was my mistake, not seeing that right there. Sorry about that. Let me put here a 1 just to emphasize the correction. Does that make sense to folks? So you were right, that should have been squared, but my earlier mistake means it should have come in this form. Thanks for spotting that. Other questions so far? Okay, last one we need is that theta. Let's make sure to color code that one. That one's not so bad because you just go right here. If sine theta is x over 5, you know what? You can solve for theta. You take sine inverse of both sides of the equation, and theta would be equal to sine inverse of x over 5. So right there we go minus sine inverse x over 5, add the constant, and then that's our work on this one. Let me put a little border here to show computations on the right, our end answer on the left. Sorry, say again?
Oh,
Yeah, that one's always kind of weird because it just seems like you're moving symbols around, but actually that's totally correct. Derivative of a sine inverse involves 1 over a square root. So if you were to check this answer, that's a required component. One thing you might notice in Calculus 2 as opposed to Calculus 1 though, the check on this sometimes is a lot harder than the original problem. If I was to differentiate this, I have quotient rule, chain rule right here, a non-standard derivative along with the chain rule. You have to simplify a tremendous amount of algebra to get back up here. So my advice is try to check if you want a challenge problem, but the better check is just a double check as you go. It's really hard to reverse by differentiating sometimes, particularly in this section. Any other questions, folks, with part B? Okay, so that's the magic of trig substitution. And again, keep in mind that when it's an indefinite integral, that's the only time you have to do this. Not exactly. I mean, we could have undone the substitution here, but if it's a definite integral, the work is very massively reduced if you just stick with the changing the limits of integration method like we did up here. Well, that's how part B goes, and these just slightly get harder and harder, but let's see how part C is next. Actually, I don't think this one's too bad, but I do have a nasty one in here. We'll take our time with it when we get to it. These are long enough, they practically deserve their own page. So there's our problem. And I'll leave it up to the class. Anyone spot the substitution we need in this situation? It's a secant one, yeah. Notice it almost doesn't feel right. There's something a little bit different in here. There's a constant in front of your variable, but actually that's not too big of a deal. We can handle that. Here's what we do. X is going to be equal to, now the a right here is relative to the 4. We just square root it like in the last problem. So we'll have a 2. The 9 right here, we need to divide by, square root it, and get a 3. So if there's an extra constant, that's the whole trick. Divide it right there. Then it'll be a secant theta. So that's our start on this one. And if you're a fan of arrows, this is how it essentially went. Root of 2 goes there. Root of 3 goes there. Sorry, say again? Yeah, this one's a little bit off. It's not in the table, so we had to make an extra adjustment. But there's 2 options here. If this seems just a little funky to you, and you're not a fan of it, you can do this. 9x squared minus 4 To make it really in the table, you can factor out the root of 9 to get x squared minus 4 ninths. Then you would take your root of 4 ninths and would come back up there. Awesome. You like that approach better? Should we give it a try or stick with what we got?
What we got, I see it.
Okay. Awesome. So yeah, there's a couple approaches. I like this approach if just trying to get it right in the formula. But at the end of the day, you kind of get the same stuff. So I'd say pick the method that makes the most sense, stick with it, and you're in good shape. Absolutely. Yeah, this one does feel like it's a shortcut when we see the actual steps here. Other questions at the moment to that stage? Okay, once you have x, that's your substitution. Now you need the differential. So let's calculate dx. The constant 2/3 stays right where it is. Derivative of secant becomes, this one's weird, secant theta tan theta. D theta. Now, next thing we ought to do is just focus on that square root part. We're going to try to simplify that down, see what we get. We're expecting to use that identity. So we're probably going to get a tangent once we square root. So let's write it all out. This is a good one to be careful because if I made any mistakes right here, we're going to detect it because we'll just get stuck at this stage. So it goes 9 square x, so that will be a 4 ninths, secant squared theta, and I never make those square roots long enough. Let's go like that. Then it'll be minus, or hang on, you know what, my work looks all right, but let me start over. And I think it's much easier when writing this out to actually start this way. 9x squared minus 4. That way we know what we started with actually. So let me unwind that. 9 times, now let's square this out and put the rest in. 4 ninths, secant squared theta, minus 4. So again, reveals why we wanted the 3 right there. It's just so we could cancel inside the root. So that's gone. Next thing we'll do is factor out a 4, and that's a clean factorization, a match and a match. That's the only reason we wanted a 2 up there. So these are kind of cool. You'll be stuck right away. You made a simple mistake. So there's a lot of extra checks on this one. It's now root 4 multiplying by root secant squared theta minus 1. So this becomes 2 root. Here's the identity down below in yellow, tangent squared. Our domain is arranged. This is an interesting domain so that the tangent function is only taking positive values. And we get 2 tangent theta. Let's highlight that in yellow. That's the substitution we're going to make on this one going here. We have a value for dx. All that's left is throw it all together. So this is the initial analysis on a problem like this one. If you were on a timed exam and you just got stuck right here, let's say it's a 6-point problem, I'd call this 3 points out of 6 because that's the whole punchline to a trig sub, knowing how to arrange this preliminary analysis. Now, once we have that, we just throw everything back in. Integrate. It's a 1 over. In yellow, we have a 2 tan theta. In green, we have dx, which is 2/3 secant theta tangent theta d theta. And finally, this is our integral to simplify. Really not too bad, but this could be a pretty tricky one in an exam setting. Let me show you what happens here. First, we're going to cancel tangent. That's nice. This 2 is going to cancel with this 2, so we'll have a 3rd in front of the integral. And we're integrating secant theta d theta. But we need an antiderivative for secant theta. That's one of those problems that's on a warm-up sheet. It goes like this. 1/3 natural logarithm, absolute value of something. Anyone recall what goes here? How about someone from the Zoom? Anyone in Zoom see what should be in the absolute value bars? I should make them longer, actually, now that I'm looking at that. That's, I think, a pretty good hint in its own right. should look something like that. It's a secant tangent with a plus in the middle. Again, pretty weird hentai derivative. It's the one that we derived, but even the derivation is crazy. You have to multiply by a weird function to make it work. But this is how I remember it. I know the antiderivative of secant does involve a logarithm in absolute value. And just like when you take the derivative of secant, you get those two, but you have to add them. So secant theta plus tangent theta. So we're just about done, but the critical step is now undo that substitution, go back to the variable x. This is pretty good progress so far, however. Any questions, folks, before we go to the next stage? Okay, well, we're back in the land of SOHCAHTOA, so let's just put that mnemonic down for comfort. I usually like to go back here, solve for secant theta, but let's just write that in as a step. Our original substitution was 2/3 secant theta equals x. So you want to solve for secant theta right away here. Secant theta is now equal to 3x over 2. Now, how can we determine secant? Well, this is the cosine part of the mnemonic. It says the adjacent divide by hypotenuse, but that's cosine. If you're doing secant, you go in the opposite order. You do hypotenuse divide by adjacent, so it'll look like this. 3x is the hypotenuse, and 2 is the adjacent side. So that's the SOHCAHTOA in action. That makes sense at the moment? Okay, if you're like me and you did no trigonometry at all over the summer break, that's what I did. This could be a little bit foggy, but it comes back with practice. You'll probably have it down pat after the homework set. So let's bring in the right triangle. Always kind of draw them the same. It doesn't have to be perfectly conveyed in any way, any proportions. It's just there to organize information, really. And let me kind of scroll back to where we need to be. There we go. So relative to that angle theta, it says the hypotenuse is 3x, and that the adjacent side of theta, that's the adjacent here, should be a 2. If you imagine, if you were solving for this side, you would square this, 9x squared. You'd have to subtract the square of that, minus 4. You would square root it, that's Pythagorean's theorem. And sure enough, that should pop right back into your picture. If it doesn't, I would consider there might be some small mistake in the problem, or maybe there's a really wild integral that could have explained it. We're not trying to do some of the crazy things. These are more the routine ones. So there's our triangle. Now we come back here and just plug in our information. Let's write this out as 1/3 natural logarithm, absolute value. First on the secant theta, notice we already actually solved that. That's just a 3x over 2 we substitute in. For the tangent theta part, we use this part of the mnemonic, which says tangent is going to be the opposite side of angle theta. So there it is in the numerator, root 9x squared minus 4. Divided by exactly the adjacent side, which is 2. Then close the parenthesis, add the arbitrary constant, and we're doing great. That's our final answer on that thing. It takes practice to get through these, but if you like a column system, it's pretty much always going to look like this each and every time. Yeah, go ahead. Oh, which part? Oh, those should be, I usually say absolute value bars. What were you saying earlier? Pipes? Oh, gotcha. Yeah, I never heard it referred to that. That's kind of cool. You mean like the vertical bar on the keyboard. Gotcha. Yeah, I usually just say absolute value bars, which takes tons of oxygen, but that's a good way to say it as well. Other questions at the moment? Okay. Again, if you want to check this by differentiating, it's a beast. The natural logarithm takes all of that, places it in the denominator. You differentiate this in the numerator. In fact, doing the derivatives isn't the hard part. The hard part is all of that simplifies, and it's a lot of stuff. The better check here is just be methodical, double check as you go, and you're in better shape. But if you were into a challenge problem, try differentiating that, and it's a pretty good review of algebra, more so than calculus sometimes. Well, let's take a look at another one, part D. Part D is going to be the last one where it's kind of a standard homework problem that you would expect. I do have an extra one just for the extra challenge. Let's see if I think we'll have time to get to that one as well. But here's part D. To me, this is the nastiest one in the whole homework set. Actually, I have a little cheat sheet here in case I lose my way on a certain part of it. But it's not hard to get started. That's the good part. Anyone see what the right substitution should be on that table? Absolutely. We have just pluses. That's a dead giveaway. We should be looking at the tangent substitution. And we'll probably use that identity right there. So that's what's going to happen to this thing. And nothing crazy with the constants this time. Here, it's just all about survive the trig substitution. We'll start by saying x equals tangent theta. The a here is a 1 squared, so we don't have to put in anything extra in this line. Next, we need a differential, dx. Derivative of a tangent is secant squared, positive. To fill out the differential, don't forget the d theta. And last thing, just write this one out. This one's pretty fast. It's root 1 plus x squared equaling root 1 plus, the x here is going to be tangent squared. Finally, we just snatch up that identity. We're taking the root of secant squared now. On the domain, notice it matches for sine and cosine. You just get positive quantities for cosine. And so this turns into ordinary secant theta. So looks like we have everything. We'll substitute this one at tan theta. We have a substitution for dx. So pretty much this is how we've done just about every trig problem. Find the right substitution or the right arrangement, integration by parts, and dump everything in. It's a load of substitutions almost every single time. That's the easy part for this one. There's something weird that's going to happen here on the trigonometry. And the reason I thought this is a good question to bring is if this happens on an exam question or homework question, I would give a hint to this problem. I'll leave it up to the class if we want to verify the hint. But here's what the hint would look like if this was a real exam question. It's by no means fair on its own, unless you consider this. We're imagining this is on a real exam. My hint would be that, let me take my cheat sheet here, that secant cubed of theta times cotangent of theta is in fact equal to some way, somehow, secant theta tangent theta plus cosecant theta. So if you see a hint like that in your problem in a calculus exam, it would mean that, well, it's a big hint. Your integral should settle to this once we do the substitution. That's a hard antiderivative in its form, and you're welcome to just drop that in. You wouldn't have to derive it on an exam setting. Well, let's see if we can bring this in and see how it all comes together. First, right here, with the square root 1 plus x squared, we're just throwing in a secant theta by substitution. Down below is a simple x, so we'll take that substitution and drop in a tangent x. And multiply by dx. That would become secant squared theta d theta. So that's how I'd run through this one. Yeah, question here? Oh, tangent x, thank you. That should have been a tangent theta. Thanks for, I think it was like a tie back there. Appreciate it, folks. Tangent theta in that location. Other questions so far? Okay, well, working through this integral, this is maybe not the nicest hint. If I was given an exam hint, I'd probably say secant cubed divided by tangent theta. But let's keep on going with what we have in this format. Antiderivative, secant cubed theta divided by tangent theta d theta. Now, one thing that's cool about trig functions is if you take tangent theta, change its base from denominator to numerator, it just turns into the cofunction. So this reciprocal function down here, the tangent theta, can now be rewritten as secant cubed theta times cotangent theta d theta. Sorry, say again? Absolutely, yeah, it can commute. You just have to change the type of function. Likewise with secant, right? Every trig function, yeah. You could take your secant cubed. Let's demonstrate it on secant. I claim that secant cubed theta is 1 over cosine cubed theta, but that's just the definition of secant, right? Secant takes your cosine, drops it down below. Now, that's not as clear as I would have liked it for what we just did. We took a tangent and promoted it to a numerator. Here's what the algebra would look like on that. 1 over tangent theta is really 1 over sine theta divided by cosine theta. Then it means it's 1 times the reciprocal of that denominator, cosine theta divided by sine theta. But then that becomes a tangent theta altogether. So every one of our trig functions, all 6, you can just switch positions as necessary, but go from function to cofunction, and you're in great shape. Other questions so far? Okay, well then I have a question for a class. This is the choose your own adventure part of the class. Should we prove the hint or should we use it? Any volunteers for a direction to go? Let's use it? Okay, so we'll take this for granted. Let's pretend it's a real exam question. Secant cubed cotangent, I'd have no idea how to integrate that. The trig identity is hard because you're not trying to simplify it. You're trying to take a trig function and write it in a way that's easy to integrate. So this is a different kind of identity for sure. But if we use it, here's what we get. Antiderivative, secant theta, tangent theta, plus cosecant theta, d theta. So we need the antiderivative of all of that. Scroll down a bit here.
What happened to the D?
Oh, that was through the hint right up here. This turns into a trigonometric identity where it's just that. Gotcha. If anyone's curious, I have, again, a cheat sheet on just that one part because that's a tricky one to get through. Yeah, go ahead. The parenthesis here?
Yeah.
That's kind of a stylistic choice. Whenever you have an integrand with multiple terms, people sometimes wrap around the parenthesis around that integrand, but it's not by any means necessary. You could drop those parentheses. In fact, let's do it this time, just to emphasize, no worries if you did. Other questions at the moment? Okay, well, let's get our antiderivatives. Anyone see what the antiderivative should be for that right there by the red dot? Absolutely, this one's just an ordinary secant theta. Now we need an antiderivative of that thing. Notice we kind of already did it. So this is how we would try to think about these things. Don't try to memorize everything in isolation. These things are sometimes grouped. Let's go up to where we did something very similar to that and show how you can use this formula, if you memorize this one, to apply it here. So if it's a cosecant instead, it goes like this. Plus the natural logarithm of the absolute value, just like the secant went natural logarithm absolute value. Take the function cosecant. There's only one change right here. You put it, well, other than the fact we're using cosecant, we put a minus in this location and then go cotangent theta plus a constant. So if you can do it once with an ordinary function, you'll note that the formulas don't change a whole lot when you go to the cofunction. Oftentimes there's extraneous negative signs and those kinds of things, but that's a great way to try to group these together. It gives your mind a lot more working room, working memory with those little mnemonic tricks. Does that make sense to folks on that antiderivative here for cosecant? Okay, well, last thing we have to do then is we need to undo the substitution. We need to go back to the original variable x. Kind of hard to show everything, but we just use that right there, x is tangent theta, and we're kind of well on our way on this. Okay, the worst thing about this one was actually the trig identity up here on the hint. So let me erase this right here so it doesn't get a little too busy on the notes. We'll pull down the substitution, x is tan theta, after I get rid of that. Far right at tangent theta equals x. I feel like I'm exposed here without the good mnemonics, so if this is helpful for you, let's put down SOHCAHTOA, because that reminds me that for tangent, the numerator is the opposite, the denominator is the hypotenuse. What's the denominator? Just go promote it to a fraction and you have a hypotenuse of a 1. Notice it should be a 1 because there's a 1 up here and an x squared. Looks like that does combine in the right way through Pythagorean's theorem. Let me zoom back in on that. Oh, I might have messed that up. So opposite. Oh, I said hypotenuse. Thank you for spotting that. That should have said adjacent. I even had the mnemonic ready to go, so that's a weird mistake to make. Good, put this one in purple just to highlight it. Should have been, I'm doing the same mistake once again, adjacent. Just got to circle that and I'll get the right thing in. There we go. Thanks for spotting that one again. Other questions so far, folks? Okay, SOHCAHTOA is meant to help, but only if I actually look at it and really use it. So O for opposite, divide by A for adjacent. Then we just reconvene on a right triangle. Here's theta. This information says opposite of theta, we'll throw in an x. Adjacent, we'll throw in a 1. And yeah, in Pythagorean's theorem, you would just say the square root of this side is the other side squared. So 1 plus x squared. Getting this back to that one part in the integrand up there. That's a very definite pattern that you can rely on. It's kind of comforting. It says everything is really coming together. All we have to now do is, well, put in what our secant, cosecant, cotangent functions are going to be. Any questions at all, folks, to that stage? Yeah.
But could you take the square root of 1 plus x squared, or is it you only take the square root of a negative sign?
It would actually have to be a multiplication or a division, unfortunately. So it's really kind of sad in algebra. This is something that turns into really huge fights where root AB is great. You get root A, root B. Division, you have the same thing, root A divided by root B. But I'm glad you asked that question because we are actually going to address this formula right here. Here's what you would have to do. Let's do a quick jaunt over to the internet. We want to look at binomial theorem for square root. See what they give us on that. So there is an expansion of the square root. It looks like this. It has infinitely many terms, so you can really do it, but it's one of those things where you're going to get an approximation because of the unending number of terms. But this actually comes up in this class. This is a type of Taylor series or Maclaurin series, what we're going to be looking at way out to chapter 11. So those are some really weird matters, but it's cool in a way because, you know, one of the weirdest functions you ever look at in algebra is a trig function. Take sine, for example. They say, well, to define the function sine, you draw a unit circle, x squared plus y squared is 1, do a rotation in radians in standard position, and pick your second coordinate. That's sine. And that is the most insane way to define a function, right? We're used to formulas. So let's take a look. Maclaurin series for sine. This is the sine function. It's infinitely many terms, x minus x cubed over 3 factorial plus x5 over 5 factorial, and so on with that pattern continuing. In fact, calculators adapt this formula in computations. They're just using the right number of terms to give the right number of precision. So calculus 2 is kind of crazy because we're really looking at what these functions actually are in a different kind of way through power series. But that's one of the weirdest things in algebra. We are just stuck here if there's a plus or a minus in that stage. Other questions so far? Okay, well, we've got our right triangle. We have our last step, undo the substitution. We just go to secant to start. That's the cosine part, which is adjacent over hypotenuse, but we reverse that. Hypotenuse divide by adjacent. That would just turn into root 1 plus x squared to start, plus the natural logarithm of the absolute value. And let's try it again for cosecant. Any volunteers for what would happen to this one? Absolutely. So you would take that one, divide by that one, and you're all set. Root 1 plus x squared. Divide by x. And now for the last one, it's always good to recognize when you don't have to work too hard. Because, I make mistakes on these kinds of things. Sometimes my eyes just go to the wrong thing, or doing it too fast. But if you notice that cotangent is just the reciprocal of tangent, you could just take the reciprocal of that right there. Not even worry about the right triangle. That would turn into a 1 over x with a minus. Add the constant, and we did it, folks. That's the trigonometric substitution on that thing right there. Really wild expression, but at least we've got it. I think this deserves a border here. Any questions at all, folks, on maneuvering through this thing? Okay, there are longer problems with a lot of weird things here. That's why in the homework set, it's not as long as about 10 problems or 9 problems. I think this one is kind of self-contained into just these, 1, 2, 3, 4, 5, 6, 7 problems. A little bit reduced, I suppose. But we have one more for the day. Let's take a look at that last one, and then we'll be on our way towards the next section, partial fraction decomposition. I realize that we're on the cusp of a holiday, so we'll try not to break that section up too much and find a natural stopping point. But here's our last problem of the day. Let me zoom into this thing. I need to learn to write smaller so I don't have to scroll up and down, zoom in and out as much, but we'll get there eventually. Sorry, say again? Gotcha, yeah, plus right in there. One thing is weird about these documents is sometimes with the right level of zoom, you can see graphical glitches or artifacts, PDF as well. So be mindful of that if you're looking at it on a small screen. Well, with what we've got, anyone see which is the right substitution? Or, well, this just looks messed up, really, right? Nothing feels like the right substitution here. What's the biggest problem about this whole integral, in your opinion? Yeah, if that natural log was gone, then the trig substitutions would be back on the table. So here's our strategy. Let's just take a u substitution and eliminate it. We're going to go u equals natural logarithm of y. So we're eliminating this part, leaving it to power 2. And if we do it just right, looks like this is on the table for us. So if that's our u, we take the differential. We haven't done this one a lot. Any volunteers for the derivative of natural log y? Absolutely, good call. This is 1 over y, and then a dy. So notice we do have 1 over y dy in our problem, so we can eliminate those. And, well, another bonus here, and it's a big bonus, is if you spot a definite integral, you get to completely skip all of that SOHCAHTOA stuff. So we'll use that to our advantage. Let's also change the limits of integration, which is a huge reduction in complexity for this kind of problem. Otherwise, we'd be undoing a trig substitution and then undoing a u substitution next. It'd be a heck of a lot of work. So let's start by saying, when y equals e, that implies we'll look up the variable y, and we're plugging it right there. New variable u is the natural logarithm of e, and this just turns into a 1 by properties of logarithms. A lot of times the numbers are just rigged to be nice, so you don't have to worry about irrational numbers in your integram. Next, for the lower limit of integration here, 1 is relative to a variable y. So y equals 1, that implies the new variable u. Plug a 1 in right there. That's my favorite logarithm to calculate. Anyone see what this should turn into? Exactly. So again, numbers are often rigged just to make it nice. We're focusing on the calculus, less on the logarithm and arithmetic. So nice friendly numbers. That's our new limits of integration. And here's what happens next. I'm going to use yellow to highlight so I don't run out of colors. But we're eliminating y over dy with a du, and that's going to turn into a u squared. So all this becomes, first, new limits are integrate from 0 to 1. By the way, if you don't like the dy being there, that's just a stylistic choice. It could have just been right here. But sometimes books save a little bit of money on printing by just pushing it into the numerator occasionally. Usually they only do that if the numerator is a 1, like in this case. So here's the du. The du took out 1 over y dy, so all that's gone. We just have our denominator, root 1 plus u squared. Now that we see this, we can more easily and cleanly see the right substitution that we have to make. But here's a line. We're now reconvening. We're imagining this is a brand new integral. We're needing to find out the best way to approach this one. If there's a plus, though, you're definitely on this line, like you were saying earlier. We want a tangent in our substitution. Any questions at all, first, folks, to this stage? Okay, well, because of the root 1 plus u squared, we're going to say x equals, well, 1's nice. That means we're just going to use a 1 right here for tangent theta. And x is tangent theta. Next thing on the list is the differential. Dx is secant squared theta, d theta. And hang on. Let me take a quicker look at this. I did make a mistake right here. Anyone see what the mistake is with an x? It should be u. Good call. Sorry about that weird confusion right here. If you have u in this problem and you're doing a trig substitution, should have been u right here. So u equals tangent theta, and du right here for secant squared theta d theta. Notice how confusing that is already. We like to say x right here to indicate we're starting a trig substitution. X came from the variable here. That's how it always starts. But if you write out u, it feels like you're doing a u substitution. We're not. We're doing a trig substitution here. Feels like it should be x, but it really has to be u because that's the new variable. Definitely not friendly, but we have to live with what we've got. So we could have fixed it if we said x equals natural log y. But then that's a reverse confusion, how it looks like we're doing a trig substitution on the first. So I'd say stick with the pattern that makes the most sense. You'll be in great shape. Well, with this one right here, it's a fine substitution. Let's write out what happens to the root. Root 1 plus u squared is going to turn into the square root of 1 plus u is a tangent, so that's a tangent squared theta. That means we're throwing in secant squared inside that root. Then this becomes ordinary secant theta with absolute value dropping off due to the domain. So those are the motions. Looks like we've got everything in a row, except for limits of integration. Let's sort that out next, and we'll be on our way. This one's a little bit trickier, so let's kind of go slow with this one. For me, I think of this as part of the review on trigonometry already in its own right. But we start out as before. Variable is u, so I'll say u equals 1. Right arrow just to say implies we're going to the next equation. If u is 1, we're plugging it right here. 1 equals tangent theta. And now that's a trigonometric equation to solve. We've actually encountered this value. Anyone recall what the angle was to obtain an output of 1 in tangent? Sorry, say again? Absolutely. Either 45 degrees or pi over 4 would work great here. I usually go with the radian measure, but if you stick with degrees, that's fine as well. Next one, not as bad if you go u equals 0. This would imply, then here's the motions. This is where my eyes or my finger on the page would be going. Whereas u, it started up here, you're just throwing 0 in that equation. 0 equals tangent theta. Now we know tangent is sine divided by cosine. Sine of 0 is 0. So that tells us, oh, that implies the angle theta is 0. Give me a moment though. I don't like what I wrote here. That's not even correct. Tangent theta is not pi over 4. Tangent theta is a function, not a number. I think what I was trying to say is that it implies theta is pi over 4. That's the better way to write it, avoiding a miscommunication. So those are, again, our newest limits of integration. I feel like this is kind of tricky the first time you see it. Any questions at all, folks, on those steps there? Okay, well, if we're happy with that, we just plug them back into the integral. So now we're integrating. First, let's change these here. From 0 to 1, notice you always want to kind of go in order, because if you flip them, your answer is going to be off by a negative sign, like we were discussing last class. So 0 up to pi over 4. Now I'm just copying in the problem until we can substitute it in the next thing. 1 over the root 1 plus u squared we see here in black turn into a secant theta. And then finally, I have this in blue right here. Du is secant squared theta d theta. That means we're on our way. This is our integral. This one shouldn't be too bad to calculate, but there's more trigonometry review on this one. Simplifying it down, it's integrate from 0 to pi over 4, secant theta d theta. Notice these certain antiderivatives come up a lot. So here's secant for the second time on these notes. The antiderivative goes natural log, absolute value. And anyone have the rest? Good call, absolutely. If it's an ordinary secant, it's a weird antiderivative, but that's the pattern. Secant theta plus tangent theta. This one's a definite integral, so we're also going to go from 0 to pi over 4. So in this situation, it's not a bad idea to go off to the margin, just calculate your secant and your tangent at whatever values are relevant. It can save you a lot of time. So I'm going to put down here secant pi over 4. Secant is a reciprocal function. You can put it in the denominator and recover your cosine. So now that's 1 over cosine pi over 4. Cosine at pi over 4 is root 2 over 2. That number is kind of awkward. We can make it fixed by multiplying by the reciprocal. That'd be 2 over root 2. And that number is totally fine. But it's more complicated than it has to be. These things just keep going. You can take 2 over root 2, rationalize the denominator by multiplying by root 2 over root 2. Then the numerator is 2 root 2. Denominator is root 2 times root 2, which is 2. Now it cancels, and you get a root 2. That's kind of nice, but honestly, I'd say that's just fine as well. If this was an exam and you used that, I'd say totally fine too. I'm not super concerned about arithmetic, especially on a timed exam. But occasionally it's fun to do that kind of stuff just to brush up on your algebra. Algebra just keeps coming back. So we know it's secant pi over 4, that's just a root 2. We know tangent at pi over 4, right on this line, is a 1. So that's probably all of the preliminary evaluations I would do on this one. Let's now write it out. Natural log absolute value, secant pi over 4. If you put just root 2 on that step, that's a good shortcut to take, but I'll fill it out for the notes. Plus tangent pi over 4, minus, now move down to the lower limit of integration. We don't need parentheses because this time it's just one term, really. So minus natural logarithm, absolute value, secant of 0, plus tangent of 0. From this line right here, we already know that tangent of 0 is 0, so that's canceling. Anyone happen to know the secant 0 value? Absolutely. Cosine of 0 is 1, so is secant of 0. So it looks like we have all of our values ready to go. It's now natural logarithm, absolute value. Secant pi over 4, we pre-computed to get a root 2. Tangent pi over 4 is exactly a 1. I'm going to leave it in absolute values, but you might notice root 2 plus 1 is positive. If you convert it to parentheses, then that's a totally fine simplification to make here as well. But just up to you. I wouldn't be opposed to you leaving it in that form. Minus the natural logarithm of the absolute value. This is a 1 plus 0. But just for the sake of the notes, let's actually take this just a little bit further. The next step I would take to end this, it would be natural logarithm. Root 2 plus 1, I probably would drop the absolute values on this to finalize the answer. That thing is just a natural logarithm of a 1, so that goes to 0. That means that really is our total answer on that whole entire process. Kind of wild, but you know what? This problem is hard to start and maneuver through, but in a certain sense, it's easier than the prior ones because we never had to undo any substitutions. We were able to just streamline it and deal with the new limits of integration as they came up. Any questions at all, folks, on finalizing that one? Okay, yeah, go ahead. Oh, that's a good question on that one. There's a kind of a lot of little steps on it, but the first thing I would do is write out natural logarithm absolute value 1 plus 0 becomes the natural logarithm of just a 1, simplifying the absolute value in the addition. But then that's the good old value for natural logarithm. Well, any logarithm of 1 would give us a 0. So that meant that whole thing just canceled out. Other questions at the moment? Okay, well, we've got 6 minutes to start that section, but that just seems kind of cruel and unusual. This will be one we come back to when we're in next class. It has probably one of my most favorite theorems in all of algebra, just because it sounds cool. That's the only reason. It's the partial fraction decomposition theorem. This is a tough theorem to read, but when we come back on Wednesday's class, you'll notice it's actually not a tough theorem to use. It's all about patterns, but saying what the patterns are in words, it takes a lot of words. So it sounds like a terrible section, but this one's not bad. It'll be a pretty easy one to get through. We've gone through some of the worst stuff with all the trig review at the same time of all the new methods. So I think you'll find that this one is kind of a lighter section compared to all the rest, despite its imposing title. So that's what we'll come back to on Wednesday's class. If you have any questions while we're getting through the holidays, don't hesitate to email. I'll always check my email in the morning, even if it's a holiday, unless my power's out or something. Yeah, go ahead.
On the end there, is it just meant a lot of parentheses? The, square root of 2, plus 1, or should it still be absolute value?
It's kind of up to your choice, but I would say parentheses is okay. Almost a simplification too, because everything here was positive. So it's like doing an extra computation. But you know, it's really totally up to a stylistic choice at that stage. If you leave absolute values in, you're always going to be totally fine. Other questions so far? Which one? Well, we only dropped this absolute value right here only because what was inside was positive, was the main reason. Well, have a great night, folks. If you have any other questions, I'll be happy to help out. And have a great weekend as well. Well, I did forget to mention for the online class and the class here as well, if you email your homework, I'll just be emailing you back the original email it came through. So expect that, just a PDF of your graded work sometime this weekend, probably Friday if I'm on track. If I lose control of my life, it usually comes in late Sunday, something like that.
Integration by parts, the first question. And I realized that like, after I turned in, I didn't actually follow the chart.
Yeah, we did want the chart for that one, but if you like, you could come back to it and put those in.
I actually wrote, I fixed.
That would work just fine too, yeah. I don't have any late policies, so if you asked a question on the assignment the day it's due, and you need to make corrections, no big deal. That'd be just fine. Sounds good. Yep.
And I fixed number 13 that I was asking you about that, our code one.
Oh, gotcha, cool. Yeah, just re-email that assignment and that'll be the one I grade.
Yeah, I just emailed it back on the same, like, reply thing.
Okay, cool, that's perfect. What I'm doing on my emails, I just put a little star on there as soon as I get a homework email. And then when I'm ready to grade, I just download them all. So if you need to make corrections, totally fine.
Thank you.
Yep, you betcha.
All right, man.
You too. Sure.
When I got through it, the signs were flipped from the answer.
Oh, I see. So that was supposed to be positive and negative.
Yeah,
And 0 to 2, y sine y. So u is y, dv sine y dy. Oh, that's hyperbolic. Oh, that might be the reason. Weird thing about hyperbolic is these are always coming out as positive, whether you differentiate a hyperbolic sine or hyperbolic cosine,
that would
the
just
signs
be
come positive.
positive.
Yeah. I think I have something here. Let me see. Yeah, under the 7.1 notes, there's a good table on the hyperbolics right here. Almost the same, but that's the odd one out. The negative sign just moves over to the right side.
That makes sense. Forgot about that.
It's weird because we're usually like hyper vigilant if
Mhm.
it's an ordinary sine or cosine function. So we're just anticipating those negative signs.